Jai Hind students, this is the 15th lecture of this satellite communication. Till now we studied various things about the satellites, that how satellite communication can be defined, what is satellite communication, how you are going to locate the satellite into the space, which kind of coordinate system you are going to use. By following all that points, we came into the picture now about the system designing. Actually, when we are talking about satellite system designing, means you have to identify your purpose, means for which kind of purpose, for which service you required a satellite. So you have to identify the satellite, its parameter, its orbital elements. Similarly, you have to design the satellite link. These all points we discussed in the previous one, that satellite link is the basically connection between the earth station and the satellite. And actually it consists of transmission system design and the transmission link design on the link budget, where link budget is the analysis or tabular form representation of the available resources to find out a individual service, how that you are going to achieve that performance. This is the example which we discussed in the previous one also, that if you want to design a maritime navigation satellite system, you can see here there is a ground station located on the earth side. This is the satellite in the space segment. These are the users, various ship in the ocean or the aeroplanes located in the atmosphere. You are using Ku band, L band for uplink downlink with them. Actually, these bands have to be determined because that is the first step towards the satellite link design. Similarly, you are also talking about the satellite link budget. That link budget is basically set of calculation or the tabular method for evaluating the power received and the noise ratio in a radio link, with the various determination of points, that antenna size, power requirement, link availability, bit error rate, or overall customer satisfaction with the satellite service. So by considering all these points, we discussed the basic concept, phenomena of the satellite link design. Now we going towards the derivation part of it. So when we are talking about the satellite communication, we have to start with the basic transmission theory, means how you are going to transmit the data from earth station to satellite. So basically this transmission theory is talking about the antenna and antenna designing. So the calculation of the power received by a earth station from a satellite transmitter is fundamental to understanding of satellite communication. Means your satellite is sending some power in the form of the signal. That signal is receiving by the earth station. So that calculation is basically related to the understanding of the satellite communication. So actually in this section, we will discuss two approaches. First one is flux density and second one is link equation. Means you have to find out this link equation and also calculate the flux density. So what is flux density? As you know that this is the earth, and from this point or from this earth or the point where the antenna is located, actually this is the outer area. If you are taking a isotropic source, actually when you are talking about isotropic source is a specific kind of hypothetical source which always radiate in all direction equally. But when we are talking about this flux density, actually this calculation of flux density from an isotropic source with EIRP. EIRP is equal to, is basically denoted the equivalent isotropically radiated power, PT. The flux density is measured over a 1 meter square section of sphere at a distance r meter from the source. Means you have a isotropic source here on the earth or something else, that having a PT power means isotropic source EIRP. From this distance r, you are taking an area that is 1 meter square or a meter square. So at that point, the power received by that area, specific area, is the flux density, that is F watt per meter square. So if you want to denote this, so at a distance r meters from the hypothetical isotropic source transmitting RF power PT watts, the flux density crossing the surface, means that is the surface, crossing the surface of a sphere with radius r is given by F is equal to PR upon 4 pi r square watt per meter square. That is about the isotropic source, means hypothetical isotropic source, which is always radiating all the power which is going to be applied to that source. So in any practical case, in any real antenna has a gain of g theta defined as the ratio of power per unit solid angle, that is the angle, solid angle, in a direction theta to the average power radiated per unit solid angle is g theta, means gain is of real antenna is defined by g theta is equal to p theta, means in power in the theta direction, radiated in the theta direction, p naught upon 4 pi watt per meter square. That is also the flux density for a individual real antenna, where p theta is the power radiated per unit solid angle by the antenna. Now we are talking about the real antenna. P naught is the total power radiated by the antenna, means that p theta is in the particular direction, but that antenna is actually radiating power in all the direction if it is a omnidirectional antenna, or if it is a bidirectional or unidirectional, then it is a total power also. So P naught is the total power radiated by the antenna, but P theta is the power radiated in per unit solid angle. Similarly, G theta is the gain of the antenna at a angle theta. Now, for a transmitter, means from where that antenna is, real antenna is placed, for a transmitter with output PT watt driving a lossless antenna with gain GT, the flux density in the direction of the antenna bore side distance r meters is, अब कितनी हो जाएगी ये? Now it is F is equal to PT GT by 4 pi r square. You can see that in that direction 4 pi r square is same. Similarly here PT GT is defining the power received, because you know that gain is equal to received upon transmitted, because gain formula is P received upon P transmitted. तो PR is equal to क्या हो गया? G by multiplied by GT. तो PT GT 4 pi r square. That is the flux density for the transmitter. Now the product PT GT is often called the EIRP, effective isotropically radiated power. That is a very important factor in this complete link equation part, and it describes the combination of transmitter power and the antenna gain in term of an equivalent isotropic source with power PTGT radiating uniformly in all direction. Means here you are taking a reference of isotropic antenna, now calculating it for the now you are calculating it for the real antenna in a particular direction. So now what is happening? Now calculation of received power by an antenna with gain GR. Now because we are talking about the receiving side, GR from a source with EIRP PTGT watt, F is the flux density incident on the receiving antenna, PR is the power delivered to the receiver. Means in the previous one you are talking about the transmitter side, now we are talking about the receiving side. So that is the EIRP or isotropic source having ERIP is equal to PT watt radiating the energy for this area, flux density F is equal to watt per meter square, receiving antenna with area A meter square with gain GR, related received power is the PR which is going to the receiver. So power is, we had a ideal receiving antenna, now we are talking about receiving antenna. Receiving antenna with an aperture of A, as dash should we collect power PR is given by F is equal to PTGT upon 4 pi r square or watt per meter square. Practical antenna with a physical aperture area of AR meter square will not deliver the power given in above equation. So some of the energy incident on the aperture is reflected away from the antenna, means reflected back from the antenna, referred as scattering. So some of it is absorbed also in lossy component. So this reduction in efficiency is described by using effective aperture AE. Means when we are talking about the receiving, there may be a chance of scattering of the power, there may be a chance of absorption by the lossy components. So that's why you have to find out the effective aperture rather than the normal aperture, a receiving aperture. So A is equal to neta A I AR meter square, where A is equal to neta A R M square, where neta A is the aperture efficiency of the antenna. The aperture efficiency neta A account for all the losses between the incident waveform and the antenna output port. So these include illumination efficiency and aperture taper efficiency of an antenna. So the total power received by a real antenna, now we are talking about the actual real antenna after consideration of that effective aperture, the power received by a real antenna with a physical receiving area AR and effective aperture area AE meter square at a distance r from the transmitter is PR is equal to PT GT AE upon 4 pi r square. That received power is in the watt actually. But again, as a fundamental relationship as per the antenna theory, you know that gain and effective aperture is related as G is equal to 4 pi AE upon lambda square, where lambda is the wavelength of the signal and it is in the meter. So put this value in the previous one, in this one, you can find out PR is equal to PT GT GR upon, because that is now for the receiving part, PT GT GR upon 4 pi R upon lambda whole square watt. That is in the watt. Now we are going towards another side, and basically this equation of receiving, this equation is called link equation. So as I told you in the starting, we have to find out the flux density and we have to find out the link equation. Flux density we already find out, this is the link equation. Now it is essential in the calculation of power received in any radio link, the frequency appear in this equation for a received power, because we have used the receiving antenna gain again instead of effective area. Actually we are talking about here antenna gain. So the term 4 pi r upon lambda whole square is known as the path loss. Means these all are the additional part and this is the losses part, LP. So it is not a loss in the sense of power being absorbed. It accounts for the wave energy spread out as an EM wave travel away from a transmitting source in 3-dimensional space. So this is the link equation in watt. So now how you are going to design this as per this definition? Recollecting that PR is equal to PT GT is equal to EIRP. GR is equal to receiving antenna gain. That 4 pi r upon lambda square is denoted by path losses. So this is about complete watt, but you have to calculate it into dB, where then PR is equal to ERIP plus GR, because that in multiplication applying logarithmic operations minus LP. Then where EIRP is equal to 10 log 10 PT GT, GR is equal to 10 log 10 4 pi AE upon lambda square, and path loss LP is given by LP is equal to 10 log 10 4 pi r upon lambda square, where this is the value. So this is the calculation part of link equation in dB. Actually the questions are coming on this equation and you have to find out these values. We will discuss later these numericals also. So now PR is equal to in further ERIP plus GR, and that loss part is also divided into 3 parts, because that are LA attenuation due to the atmosphere, LTA losses associated with the transmitting antenna, LRA losses associated with the receiving antenna. So these all points are also going to be considered. So now this is the basic transmission theory, and it is going to design all the system. You can see here, now you have a link equation. That link equation is first of all giving us about the transmitting antenna parameters, that is coming from the ERRP, PTGT. Now that loss related to the transmitting antenna is also calculated here, LTA. Now the path, because that atmospheric path is also giving the losses, and that is the path losses, LP. Similarly, atmosphere losses, LA are also there. Path loss is related to the satellite path, but atmosphere losses are related to the atmospheric condition. Then as per the link equation, this is our receiver side, where we are using low noise amplifier, and the received power to this low noise amplifier is a PR, which is getting it from the link equation, and the losses related with this receiving antenna is the LRA. So these all are the diagrammatically representation of this satellite link equation. So this is all about this basic consideration of various satellite links, and you discuss these points. So in the next one we are going to discuss about the G/T ratio and all other things related to this part. So till then, thank you.